All right, I see the light on. I see no students, so I can speak to myself. So let's make an effort to finish this discussion on the exponential family. I'm not going to do the whole lecture. And then we will proceed with an extremely important topic on latent variables. So I remind you, the exponential family was defined, if my pointer works, from this nice equation in terms of the natural parameters, eta, and the sufficient statistics u. And today I want to basically discuss a little bit about prior models from the exponential family, and in particular conjugate priors, and then show you some basic examples why everybody is working with exponential family distributions, just to show you that somehow you can generalize results to include many things that will not be possible for other distributions. Okay, so imagine that you have a likelihood model given by this equation. Okay, so we're asking, can we find a prior that is conjugate to this? So in other ways, can we find a prior that if we multiply with this likelihood, we will get a posterior that will look exactly like the prior, but with updated parameters? And the answer is yes. Here is the general form of a conjugate prior for this exponential family of distributions. So here we have a g of eta. So we're going to have g of eta to some power that I indicate here as mu 0. So all the coefficients for the prior have a 0 subscript. And then you notice here you have exponential of eta transpose u. So you will need something of the form eta transpose tau 0, where tau 0 is some constant. Okay? And if there was you remember there was also another factor here that I put things in proportional, and if I bring this factor in, okay, effectively I can, you remember this form, right? All right? If I want to write this with the A term, I'm going to have exponential of eta transpose u minus what? What is A? Remind me what is A? A of eta, by definition, for the exponent. Log of g. So if I bring g inside, I'm going to have e of minus what? Of minus a. All right, so the prior is going to be of the form e to the minus a times some coefficient. And you say, I don't believe any of this, and we will see that if somehow we multiply, right, the likelihood, you're going to get g, and the exponents are going to come together nicely. So mu 0 will be updated, and then you can see the sufficient statistics will come nicely, because the sufficient statistics here are tau 0, here are u, so if you put the two together, you get u plus tau 0. Some notation that is going to be clear on the next slide. I am going to define a new tau 0 that is going to be such that tau 0 equals some other coefficient mu 0 times tau 0 bar. Right now it looks completely arbitrary, but on the next slide you will see why you may want to introduce, instead of tau 0, to put mu 0, tau 0 bar. I mean, you substitute one constant with two other constants, and one of those constants is this mu 0. So we will see how this thing comes on the next slide. So there's no limitation here because this is arbitrary, right? This is arbitrary, but I define tau 0 bar to satisfy this equation. Okay, so let me multiply so I'm going to assume that I have a likelihood with n data points. So I will multiply my likelihood for one point n times. So I'm going to have this product of these h of xn factors. I am going to have g to the power n, and then I'm going to have exponential of eta transpose sum of all u's. You see that? Right? You get u of x1, u of x2, all of them are summed together, so you're going to get sum of all u's. And my prior, again, is given as proportional to the exponential of eta transpose nu 0 tau 0 bar minus A times nu 0. Okay? Where did A times the nu 0 came? It came because you remember A is minus log of G, and here I have G to the power nu 0. All right? So you get minus A times nu 0. So multiply those two, all right, to get the posterior. So what will you get? We are only looking at things that involve the parameters, so you're going to get G to the power n plus nu 0, and then exponential of eta transpose, summation of all the u's, times nu 0 tau 0 bar. Now, I am going to introduce u bar, that is basically the sample mean of u, all right? So will you agree that this summation is going to be n u bar? So can you see now why I introduced that constant tau 0 to be nu 0 tau 0 bar? Because I wanted to make it to look similar, right? I wanted to make it to look similar to what I had in the likelihood. So if you write it in this form, effectively nu 0 is the number of pseudo measurements introduced by the prior, right? So in the likelihood I have n measurements, each of them provides a u bar contribution. The prior I have nu 0 measurements, and each of them provides tau 0 bar contribution. That's why in this exponential family of distributions, right, you can put a physical meaning to the coefficients that you have in the prior. Not that you need it, but there's no other distribution where you can do it. Here you can do it because you can see the analog of capital N with nu 0 and u bar with tau 0 bar. Okay? All right, so immediately you can see that this distribution, right, it's in the exponential family. I see g of theta to some power, exponentially transposed to some sufficient statistics there. And obviously immediately you can see that the posterior, it is in the same family where the coefficients have changed now. These prior coefficients, nu 0, tau 0 bar, they're all updated. And what you see on the bottom are tau bar subscript n. You can see nu subscript n, so nu 0 changes to the total number of counts. And the distribution basically is of the same form with updated parameters. So effectively, you know what? If you already know that this is an exponential family distribution, you can actually guess what these coefficients will be, right? And write and say the posterior is without any calculations. Okay, but it didn't take as much of effort because effectively we multiply the likelihood with the prior, and the multiplication was straightforward because we have the same terms with different exponents, so we can just add the exponents. Okay, so nice. The posterior is in the exponential family. Let's see more nice things. Can we write for any distribution in the exponential family the posterior predictive distribution? The answer is yes, and I think I may already have done it. Maybe not showing to you in the very general form, but let me just remind you what is the predictive distribution. So capital X is my previous data, right? So I use capital X to compute the posterior of theta, and now I want to make predictions. I want to know what is the probability of new data X prime, right? Isn't it that, so what is the probability that I will see data X prime coming from this distribution? So the predictive distribution, again, P of X prime, before instead of X, right, in a lot of our earlier lectures, we had D, right? Here indicated as X, okay? So what is the predictive distribution? What is that first term? That's the likelihood times the posterior, and then we average over all sets of parameters. And instead of using eta, because theta here, I take it as a function of theta, I use this directly, the integration in terms of theta. So let me see where the different terms come. Would you agree this term comes from this likelihood term? Right? The first one, we agree? All right. Where is this term comes? these two terms together, it's also part of the likelihood of x prime, correct? The two terms, right? The second and the third. All right. And what is the last three terms? What is this and this and this? We just proved that the posterior of theta is what distribution? It's in the exponential family with those updated parameters. All right. And what is this denominator there? Is the normalization factor of the posterior. All right? And what is that? Is basically the integral. I gave you various forms of this, right, for z. But it's effectively, if you normalize this in x, you know, you get the normalization factor. But I gave you nice forms in terms of a and g, etc. So, again, these three terms come from the likelihood. This comes from the posterior. And so let me multiply the term from the likelihood with the terms from the posterior, and pay attention, the posterior involves capital X, the likelihood involves x prime. Everybody understands why? We computed the posterior after we collected data x, and now we want the predicted distribution for x prime. Right? So the likelihood is for x prime, is the likelihood of x prime, but the posterior involves only the data x. Okay? So if you multiply the two things together, you effectively, and you move the integral, so the integral becomes integral of this g times this exponential, where eta transpose this u plus tau 0 is now added to ux prime. And if you look at that integral, what does it tell you immediately? That integral is the normalization factor of what? Of another distribution from the exponential family. With what parameters? With sufficient statistics u of x prime and u of x plus tau 0, which you see here. And what coefficient nu is n prime plus nu subscript n, which is nu 0 plus n. All right? So effectively, the predicted distribution is some, coefficient that doesn't depend actually on any of the parameters of the distribution, and then the ratio of two normalization factors. Does this remind you anything? Remember when we did some simple examples before, and I show you how you can actually you can compute. The fact that you have these two normalization factors, does it remind you anything? Have we seen anything like that before? Where? Where did we have ratios of normalization factors? I gave you a general methodology to do some computation from the posterior of the parameters to compute the marginal distribution. Remember, if you take the posterior being the likelihood times the prior divided by the marginal, and you substitute everything in terms of the dependency in theta and normalization factors, then you get that the marginal is a term coming from the likelihood divided by 1 over the normalization of the prior times the normalization of the posterior. Does that click at all? So actually, that formula that we saw derived from the posterior, you can derive it here as well. If you assume that you had no data before at all, so if you take capital N to be equal to 0, then you actually you define the marginal of x prime. So basically the formula that I had shown you before for the marginal, you can derive it here using this formula for n equal to 0. So you did not have any data before, and so you compute only the posterior, and if you use the normalization factors from there, you can actually, for n equal to 0, you can get, this will give you the marginal likelihood of x prime. This is very nice, right? You can actually compute the marginal likelihood directly in terms of normalization factors. You can compute the predictive distribution directly. Now, also these formulas indicate to you because these normalization factors are very complicated, okay, indicate to you that when it comes to computing the predictive distribution or the marginal likelihood to do model selection, the problem is not easy. But unfortunately, that's the only problem people in Bayesian statistics have in machine learning, because the rest of the problems are too easy. Okay, so really, this type of calculation is extremely important, but I'm saying is, if you want to do calculations, how exactly, I am writing Z there, but if you have to compute Z, that's not a trivial task. Okay? All right. I have an example that actually we had done in the very early part on Bayesian inference, so I'm not going to repeat it, but we use that formula that I just described with words for if you have a Bernoulli likelihood with a beta prior, you basically can derive the marginal likelihood in terms of ratios of normalization factors, so you may want to actually look on this slide as another example. Okay, a little bit about maximum entropy. Huge subject in machine learning. There is actually a book, a very famous book on probability with the title Maximum Entropy, written on the subject topic. So I'm only going to give you one slide, unfortunately. Okay? So first, what I want you to remember about these maximum entropy distributions, that basically they're distributions from the exponential family. Okay? So that's the first thing to click. And they're used as prior models. And when do you use them? If you somehow don't have any knowledge about the prior, right, about what to put in there, this distribution that maximizes the entropy of the parameters is basically a preferable prior, and it's called the maximum entropy prior. So I'm going to give you the general form with not much discussion. All right. So if you take a discrete, let's say some variable theta that takes discrete values, the entropy, for those who have not seen this before, is defined like that. If the variable is continuous, the summation becomes an integral, so that's the entropy. If you assume that somehow you know something about some moments of that distribution of theta, so if you have described, let's say, the mean or the variance or the kurtosis or some higher order moments, usually the constraints on those moments are written like that, right? So you know some expectations of some functions of theta. So this G of theta can be just theta, so you describe the mean, can be theta squared, so you describe the second moment or the third moment, right? So if you have some statistics like that fixed, then you can show that the distribution for theta is given by this wonderful formula, all right? That may somehow, for some, may remind you like a softmax type of distribution. That's not what it is. All right, so it's a distribution from the exponential family, and what those parameters lambda are, they are Lagrange multipliers that enforce the constraints that you have in the moments. Okay, so these distributions of maximum entropy are extremely useful when you say, look, this is what I know. For the things that I don't know, I want to make them as random as possible. I want to maximize the entropy. And what does that lead you is to an exponential distribution of this form. So let me look at the Gaussian. Can you put me the Gaussian in this form? So is the Gaussian a maximum entropy distribution? So let's say I have a distributions with a given mean and a given variance. What is the maximum entropy distribution when I give you the mean and the variance for a continuous variable, you think? It's the Gaussian. All right, so now you know another reason why the Gaussian is such an important distribution. If you prescribe the mean and the variance, all right, then the Gaussian is the distribution that maximizes the entropy. Okay? Again, really to learn more about this, you will have to read a serious book on Bayesian statistics, and I have the book by Roberts here, has a very nice chapter on this type of topic. Okay, so let me finish now by repeating this integration that we did of generalized linear models with the exponential family. Okay, so maybe if they did not click on this earlier lecture, maybe today they can click, and I'm going to do an example, one example in the context of regression. And we have seen regression, in the very basic setting very early on in the course. So assume that you have input x and output y, right? So I give you some data of x and y, and you want to fit some regression function, but you want to do it probabilistically. And I remind you, the regression function was the mean of the conditional distribution of y given x. Remember, when you try to fit, right, and you have different data for different x points, the regression function is the mean. For a given x, is the mean of y. And the simplest model we took was to make that distribution a Gaussian. You remember? With some noise beta. So I want to basically revisit this problem, but in the very general case where this distribution that I use to describe this conditional, where basically my regression function is anything to start with. Okay, so what I'm going to do is I'm going to introduce some variables first. Remember, the regression function, remind me, what was the Gaussian model, right? So what was the distribution of y given x? So what was the likelihood for given x? What was the distribution? Give me the exact form. What was the mean of that? Like the most basic linear regression model we did. What was the mean for a given x? I'm looking again for the probability of y given x. What was, in the most simple model, what was the mean of that Gaussian? You are running too much ahead of me, so I don't follow. So what was, somewhere we have to introduce a linear model, right? So what was the easiest linear function we can use for the mean, for the regression function? What was it? In terms of some parameters.
Theta Tx.
Say it again?
Theta x.
So W transpose x, right? So that was the easiest thing, and if you want to have W transpose of phi of x, that would be another thing, but the easiest thing was W transpose x. Okay, so the W, I call it here theta, to just follow the notation from the literature. So Xi that you see there is basically is theta transpose x, is W transpose x. Okay, so that's my variable Xi, and so when we did the introduction to regression, the regression function was some function of theta transpose x. All right, and the easiest function, as we just said, would be theta transpose x. But generally speaking, the mean of the conditional distribution is some function of theta transpose x, and I indicate that function with these arrows here. So f operating on theta transpose x gives me mu, and what is mu? What is the regression function again? For the conditional distribution of y given x? What was the meaning of the regression function, right? We took that the response at every x is around the regression function with some noise. But if I remember, we call it beta, right? The precision. So what is f of theta transpose x? What is mu? It's the mean of the response at x. All right, so mu is the mean of the response at x. All right, so mu is the mean of the response at x. Now, hopefully you did not forget about this. If we work with distributions from the exponential family, not just Gaussians, you remember that we proved that there is a one-to-one relation between the moments, so mu, for example, and what else? So if we have a distribution from the exponential family, there is a one-to-one relation between the moments, like mu and the natural parameter theta. So that function psi that you see there, it uniquely identifies the particular distribution that we have in that exponential family. It's given, right? If you have Gaussian, you know exactly what psi is. All right, so let's summarize. We define this variable xi that is theta transpose x, like w transpose x, that's what we had before. Then we define the mean of the predictive of the conditional distribution at x, which we call it f. That takes me from xi to the mean. And then we said there is a unique relation between the mean mu and the natural parameter theta, and that relation is defined by this function psi. I want you to be sure you understand this picture because the rest is actually trivial algebra. So is there anything on this picture that doesn't make sense? So again, we're looking at the conditional distribution, right, of y given x. We're doing regression. So the general regression model will define a conditional distribution with a mean that has this form where f is some function of theta transpose x. And then if my distribution is an exponential family distribution, there is a unique relation between mu and eta. And the function that takes me from mu to eta is psi. Here is now the deal. So f can be anything you want to, right? You can put any function, but if you're working with the exponential family, there is one particular choice of f that makes the algebra extremely trivial. And you remember from a previous lecture, what is that choice of f? So if you work with the exponential distribution, means psi is given. So what is that particular form of f in terms of psi that makes the problem very trivial? The inverse of psi. All right? And let me just go directly on this picture. So effectively, if f is the inverse of psi, means that xi and eta are the same, right? Because mu is derived forward by f of xi, and mu is also defined by psi inverse of eta. So f and psi inverse have to be the same, okay? And you see this, xi and eta are the same. So this choice of this regression function is called the canonical choice. And I'm going to show you now why, if you make this choice, every algorithm in the whole exponential family becomes actually trivial and very well recognized algorithm in machine learning. So I'm going to do one example. This is the same example, actually, sort of, I tried to do like 2 lectures ago, and there was some scaling that I had introduced. So I removed the scaling from this slide, simply just to keep the notation clear, all right? So I am just, I'm only giving you a warning that you may have to actually divide, for example, this whole term here by the variance if you work with a Gaussian. But really, at the end of the day, that scaling doesn't do anything. So if you forget to put it in, it makes no difference. All right? So let me see what we have. I want to define, I want to do maximum likelihood, right? So I want to find the maximum likelihood estimate of the parameters. So let's see how that maximum likelihood estimate may look like. So I'm going to start with data that involved pairs of x and y. All right, so this is my data set. And I'm going to write down the log likelihood. So I want you to look at this form and tell me every term from where it comes. Look at the exponential family that we had before and tell me if you agree that this is the log likelihood. So where is the first term came from? Where did the first term come from? Look in your nose, right? If you have the computer, what was the form of the exponential family of distributions? So we're right, the likelihood comes from there. So look and tell me that the first term will look like this. what I want you to actually be sure you don't get confused here, right? My data are not, I don't treat X as, X is the input. I am looking, remember, for the distribution, the conditional distribution of Y given X. So really, my data here are the Y's. I mean, X is also given, but I want for a given X to find what the Y is, what the mean value of Y. And I am giving measurements of Y. So if you look at the exponential family, each term will give you log of H computed at Yn, because that's my data point. Right? Just be clear, it's not X, it's Y, because this is what I'm interested in. All right. Now, you remember in the exponential family, you have eta transpose U. So what are the sufficient statistics U here for every data point? It's Y. All right, so I just wrote it directly, eta times Y. Okay? And you will see shortly why I put a subscript on eta, because eta is going to be different for each point n. And then I had minus a, right? You remember in the exponential, if you put z inside the exponential, you have minus a computed at eta n. So a little bit of parenthesis. Why can somebody look at the equations that I have here and explain to me why I put on eta, I put a subscript n, why eta is a function, it varies for every point? Let me just go back. Eta, if I use the canonical approximation, eta is equal to what? We just described this before. Eta is equal to what? Eventually, so when you do this, eta is equal to xi. And what is xi? Is theta transpose x. So eta is going to be different for every point x. Right? This is, it's tricky. For this, the choice we make, eta has to be with a subscript n, and that's exactly what I have here. Okay? So eta subscript n, yn, minus a of eta n, and I wrote here all the equations. Okay? So this is my mean, okay? And xn is given theta transpose xn. All right. Now, don't look at the equation below. So what is zeta in my problem? I just told you, actually. If I use the canonical approximation for my regression function, what is zeta? Xi, and what is xi? Is theta transpose xn. Theta transpose xn. You see that? Right? Eta is theta transpose xn. All right. So the log likelihood takes this term plus that term minus that. I am ready to actually do maximum likelihood estimation. Okay? I'm going to take derivatives with respect to theta of every term. This term does nothing. There's no theta. What's the derivative of this with respect to theta? What it is? What's the derivative of this term with respect to theta? Xn yn, right? The summation of xn yn. And that's why actually you notice that I call this the sufficient statistic for theta. So it's very nice actually. It tells you that the inputs and the outputs together as a product, right? That summation is what you need to be able to compute theta. This is actually amazing that you get some result that looks like this, okay? So this is, comes together nicely. And then, so this is what I have here. When I take one derivative, I have yn xn. And what's the derivative of a with respect to theta? If you tell me that, you make me happy. What's the derivative of a with respect to theta? You remember I derived for the exponential family, I told you how you compute the moments. So the first derivative of a with respect to eta is what? It's the mean. It's the mean. And then what do we need? We need, the first derivative with respect to eta is the mean, mu. All right, that's there, mu n. and then I need the derivative of the mean. All right, I need the derivative of the mean with respect to what? With respect to theta. Okay? Now, where is that xn comes from? So I need the derivative of theta with respect to theta. I need the derivative of eta, right? That's the argument there, with respect to the parameters theta. But you told me that eta is equal to what? Eta is equal to what?
C.
To xi. So the derivative of eta is the same as the derivative of xi with respect to theta, and what is that?
X.
X. Done. And this is this amazing formula that appears in all algorithms that you can see for maximum likelihood. It has effectively has a summation, but you can even forget the summation if you do this one data point at a time. Has the error between your data and what your model says, right? Because mean comes from the regression function that you use. So that's the error times the input point xn. And that formula appears, we have seen it 50 times. And we can see it another 50 times because it's a universal formula for when we play with the exponential distribution. With this particular choice of regression function being the canonical, following this canonical assumption and having f equal to psi minus psi inverse. Okay? So again, if you're going to do stochastic optimization one data point at a time, you're going to write one line of a code and you're going to say theta is the previous theta minus this gradient. The error times xn, and you keep going through the data points until convergence. So I can write this in a matrix form using the design matrix X transpose Y minus mu. All right? And I'm not going to do the algebra because already we have done it actually, So if you want to compute the Hessian, so if you want to take second derivatives with respect to theta, what term is actually, where is the second derivatives coming in? They only come in mu. All right? So the second derivatives will involve the derivatives of mu. So if you calculate the Hessian and you use Newton's gradient optimization method, effectively you get the algorithm that I highlighted in an earlier lecture. And what name we gave to that algorithm? Where it looks like least squares, but not quite. What's the name we use for that algorithm? We put a buzzword in front of least squares, right? The MLE estimate is like least squares here, but there is this weights W, and this weights W depend on the parameters themselves, so you have to iterate. So what's the name for this? How do we call this? Oh, it's written there. Iteratively reweighted least squares. Okay? You can start, using these techniques again for classification problems, for logistic regression, for many different settings. And the nice thing is you don't limit yourself in one distribution. You include all of them, all right, under this general umbrella of the exponential family of distributions. Okay? And again, because this is important for everybody who is going to work on stochastic optimization and deep learning, all of these algorithms, when you see an update that looks like this, the error times xn, right, where the mean is computed through some model, all right? Just remember that there is a very good chance that this calculation came directly because the distribution of interest is the exponential family distributions, okay? And rho here is just a learning rate. You can put anything for now you want to, but again, this is the error between your data, your prediction point, n minus what the model, this is your data minus the model prediction times xn, right? A very sort of universal formula in machine learning. Okay.